Hi, so today's topic is finding linear and differential paths in ARX ciphers using nested research approach. I tried to prepare the presentation in a simple way for general technical audience, but of course a little bit background in crypto may be required. So let us start with the first slides with some basics. A cipher is an encryption algorithm that takes some input text and provides output in encrypted form. It uses several components such as substitution box, here it is, and permutation box, this one, or some other operations along with hidden keys to encrypt the data. According to Kirchhoff's law, the design of the cipher, such as substitution or permutation specifications, should be known to everyone and key must be hidden. I remember when I started my first course in cryptography during my master's, I thought why we don't hide algorithm to make it more secure, but later I realized for cryptanalysis purpose, design should be public. This is just like when a group designs a software and other group performs testing to find bugs in the software. So basically, a cipher treats like a black box once we apply a secret hidden key and we don't know how data is encrypting inside the cipher. Here we take an example of substitution permutation cipher where each round consists of a substitution box, this one, a permutation box, and a key addition. S-box works like a nonlinear layer while P-box is just a cross-wiring and work like a linear layer. So here we are trying to find a path how data is flowing inside the cipher. You can see with black lines. We take some bits, for example, P5, P7, and P8 or any other subset of plain text bits and see how it is passing through several rounds. Uh, but note that this is not the actual bits. It could be a subset. This is not the actual input. Here, once we apply a secret key, cipher works like a black box, and therefore we can only try to find most probable path based on design of the cipher. So, um, whatever you can see here, the path is not the actual path, but this is the most probable path. So basically, for linear cryptanalysis, our goal is to find a path with higher probability that can be used as a distinguisher to make an attack. Therefore, we try to find a probability linear relationship between a subset of plain text bits and subset of data bits in the last round. When we try to find a path, the biggest problem is created by nonlinear layer, which is S-box in this case. So let's say if the input of S-box is x1, uh, so you have to find the most probable output of this S-box. And for that, we create the linear approximation table with the help of S-box table. And this column shows the inputs of SBox and this row shows the output of SBox. And these values are called bias. I will not go in detail, but we can say like this: if you have an input B and output 2, then it has a highest value. So it is a most probable transaction through SBox. Now let's see other inputs. If your input is 4, so you have to find most probable output with input 4, and in this row this value is 6. So we can say 6 is the most probable output. So I remember one more question arrived in my mind when I was first reading about linear cryptanalysis, that why we are creating this approximation table. If we consider x1 as input, it means um, x1, it means this is 8, and we can find the output from the S box table. So for 8, the output is 3. But this is wrong. The answer is again the same. The cipher is a black box and we don't know the actual input. We are just considering an active bit. It might be possible your actual input is x1 and x4. But because we are considering this bit, so we have to find which output bit is most probable. Now, what is differential cryptanalysis? Here we discuss about the differential cryptanalysis. This is similar to linear, but here we take two inputs and pass them through cipher rounds and try to find how differences propagates through encryption algorithms. Encryption algorithm. So you can see here this is one plain text P2 and this is another plain text this is one plain text P1 and this is another plain text P2, and we are trying to find how the difference of both are propagating through cipher round. So the only difference is here we are trying to find how difference is propagating, while in linear cryptanalysis we were just simply looking how a simple plain text is uh, flowing through cipher. So in case of differential cryptanalysis, we create the difference distribution table. This one is a difference distribution table, and we do the same like for if we have input 2. So we try to find out the biggest value in this row, and here it is 6. So for input 2, the output could be 5. Now here we talk about the ARX cipher that provides lightweight encryption because they use a very simple operation such as addition, rotation, and XOR. So these operations are lighter than substitution boxes in terms of memory and power, and therefore suitable for IoT devices. Now here the nonlinear component is this addition modulo. Therefore, we need to analyze this operation to find which could be the higher probability output for some input. So you can see here if this one is the first input and this one is the second input. So after applying this addition modulo, what could be the most probable output from this layer? Therefore, we need to analyze this operation to find what could be the high probability output for some input to find a linear or differential path. But here is the main problem. For 4-bit SBox, the size of linear approximation table or difference distribution table is 2 to the power 4 cross 2 to the power 4, that is equal to 2 to the power 8. But uh, but in general, the word size in ARX cipher start from 32-bit, and it could be more like 48 or 64 or more and so on. Therefore, generating a linear approximation table or difference distribution table for modular addition, it requires 2 to the power 64 or more elements in the table, which is almost impossible, or we can say infeasible. This is more or less like you are standing on a road and you have 2 to the power 32 paths, and you have no idea which path you should take to reach your destination. Um, Finding a good differential path with relatively higher probability is a kind of problem where we face a huge state space and there is no clear and obvious way how we should make the next step. Certainly, we find this kind of problem in many different areas, especially in artificial intelligence. Such type of problems are very common when you have a lot of options and you need to choose one. So I was inspired by some artificial intelligence algorithms and tried to find how these algorithms solve such problem in other areas. I was searching and found a paper where author solved such type of problems using nested Monte Carlo search, and they have initially used their algorithms on single player games like Sudoku and successfully applied. So it's like you have a tree-like structure and you have several paths from level 0. So from level 0, you try all the possible paths to reach level 1. And after level 1, you just make a random path until you reach the leaf node. So like here, you are just making a random path. And next time, you can see here the highest value is 30. So next time we start from this node at level 1 and go one level down by trying all the possible paths from this point. And then we again make a random paths from here. So you do it again and again until you don't find required results, but it does not guarantee that it will always provide you the optimal solution. However, it was not possible to directly apply this algorithm in our case because if you consider this this point to make a decision, so if we consider our cipher, so we have to choose one path among 2 to the power 32 possible paths. So we cannot directly apply this algorithms in our case. But I was inspired by this and created a new algorithm that was suitable for ARX cipher cryptanalysis. So in the next slide, I will explain you that. We call it nested tree search algorithm that is based on running many random simulations. For simplicity, let's say you are in Lingvi and uh, our goal is to reach Paris or close to it. We have no clue about direction, paths, or anything else. So let's say we choose a random path and reach Prague. From Lingby, we choose a random path and let's say we reach Prague. Then again we take a random paths and reach Vienna. And finally, again with a random path, we reach Warsaw. And uh, we calculated the distance or someone calculated distance for us and tell us that we are 2000 kilometers away from Paris. But don't take these directions seriously. This is just or this this is just an example in the slide, not actual distance. I'm just I just took it for explaining you. So we memorize the previous path like Lyngby, Prague, Vienna, Warsaw. We already memorized this, and next time we start from one level down. From here, uh, we start from Prague and again choose a random path. We go to the Bern and then Zurich, and then someone told us that you are 1000 kilometers away from Paris. So of course, it's this path is better than the previous one, and therefore this time we save this one and forget about this. Now, we again go one level down uh, by following the best path, Lyngby, Prague, and then Bern. And from Bern, um, we make a random path. Let's say this time we reach Brooks, and our distance from Paris is 500 kilometers, and therefore we again update the path. So our final path is Lyngby, Prague, Bern, and Brooks. We again start in the next round because this is called a nested tree search approach. So this was the one loop, and again we start from Lyngby and follow the best path and do the same process until we don't get required results. So basically in each trial we are trying to find better path than the previous memorized one. So you can see here what is the difference from the previous nested Monte Carlo tree search. From Lyngby we are not trying all possible uh, paths, but we just take a random path. So each level we are just making a random path and we are trying to find better than the previous one. Let's take another clear picture of how our algorithm works. Uh, Here we have a complete tree. You can see all the paths, you can see all the distances or weight assigned to leaf nodes. So, but you can see I don't know what is the actual path. So let's say I'm here uh, at this level 0. Uh, First time we make a random path A, B, D, and the weight of this path is 2. So initially the current path and best path list was empty, and because first time we find something, so we save these values in current path and again in the best path. And here our goal is to reduce these points. So let's say if the first time it is 2, so our goal is to move it towards 0. So first time we save paths in both lists because the current path and the best path are same. Next, we go one level down and by following the best path and start it from B and make a random move. Let's say this time we make a different path and reach leaf node. This time our new path is A, B, E, and weight is 1, which is better than 2, and therefore we save it in best path. We modify the elements of best path and we save the new path here. It's better than the previous one, therefore best path is again updated. Next time we again go one level down and we start from E, and let's say we again found the same path our which is same as the previous one, and therefore we don't update it. This is same as the previous one. Now there are several applications of this algorithms for ARX ciphers, and we can apply for um, I have I have applied it for spec cipher and Simon cipher, and then I also tried to with Lia cipher, but it can be applied with several other ARX, and it's a great uh, heuristic, and it provides a state-of-art result similar to other results already published.